Good. All right. Afternoon, Victoria. All right. Let's get going. So that because it's been raining, uh, uh, Dora and I have been out lots of times, but I haven't been taking pictures in the rain. You've already seen her in her raincoat, and we haven't got to any nice parks and that sort of thing. So, but the weather's supposed to improve tomorrow, so maybe next week I'll have some pictures for you. So I needed something to start out today and thought, fine, I'll take an example from at the end of chapter 5. There's a graph there. I can't remember what it shows, but it's taken from a site called Spurious Correlations. And it's an amusing site, at least amusing for people like me. Um, it The fellow has taken time series data. We haven't done time series analysis in the course, and it's not on the agenda, but I think down the road maybe I should. It's data that's collected over time, and often we see patterns over time among two different things that seem to have the same pattern, but they're not related. And what we see is correlation, but not causation. And so I was on their site today, and this was a graph of the number of Japanese cars sold in the US between 1999 and 2009. That's the red line there. And it matches very closely with the number of suicides caused by people crashing their cars. That very, very high level of correlation. But I don't think you would think that when just because there are more Japanese cars sold in the US in a given year, we're going to see a jump in suicides. Or if we stop, if the US stopped selling any Japanese cars, suicides from crashing your car would plummet. But interesting how the two patterns match up. And their website has tons of examples of these types of things where two things seem to move together, but they're not related to each other. And it is a constant issue. Be careful when looking at data and when you see a pattern that's there. Is there actually a relationship between the two variables? Can you explain why you think the two might be related to each other? It may be a third factor that's causing both to happen. This is sort of related to last week's discussion question, where it was noted that students that take a full course load each term have a tendency to graduate sooner. Well, that's kind of nice. And yeah, it's not surprising because they're taking more classes. But that doesn't mean that you should be pushing students to take more courses each term. A student that only takes 3 courses or 4 courses or only 1 course does it for a reason. More often than not, it's because they don't have the finances or they have other commitments that preclude them from taking more courses. That we have at St. Mary's, historically about 3/4 of the students have a part-time job or are actively searching for a part-time job. It's interesting at Dalhousie, it's the other way around, only 25% fit that sort of description. And it reflects very much the socioeconomic status of our students versus Dalhousie. Our students have to work to go to school. They don't have a choice. They don't work just because they feel like working. They'd much rather, if they had the money, they wouldn't have a job. They'd just go to school full time and enjoy themselves and get their degree quickly. But either they don't have the money or they don't want to graduate with a huge amount of debt. And so they're making financial decisions that impact their program. And so it takes them probably an extra year to graduate, but it's the only practical way they can do it. Dalhousie attracts a lot of students, particularly from Ontario, that have the financial resources to be able to go through school, not have a pile of debt at graduation, be able to party a lot more. So it's not cause and effect. They're doing it because of some other type of factor. So be careful about this issue of causation and correlation. And it's always something you've got to keep in your head before you jump to a conclusion about cause and effect. So a little bit of feedback on several different things. The test number 2, there was a request that I explain each of the answers. So I've gone into the test, and after each test question, it should have text information explaining what the right answer was and why it was the right answer and why others may not be the right answer. And hopefully that's helpful in interpreting what went on within that. In reviewing the questions on that test, several probably weren't appropriate for a multiple choice test. Or maybe they're just a little more difficult, and the test was more difficult than I had intended. That in my head, when I make up a test, I have a certain average in mind as to what I hope we're able to achieve on it. And with a very large class, and our class is large enough to be considered a large class, if there's a gap between what I expected and what happened, it's usually the fault of the test. It's not the fault of the student. I don't get that many students all going off or being lazy or not doing something or whatever. That generally doesn't happen with a large class. And so it's the test's fault. So I'm grading it out of 15 instead of out of 18. So a passing grade would be 8 now instead of 9. That if the average was around 11, I think, on the test, so 11 out of 15, probably about a 70% or thereabouts, and that's where I wanted the average to be. So it doesn't change your grade in Top Hat, but when I go and calculate final grades, I'll download the data from Top Hat into Excel, and I'll do all the number crunching to work out averages and that sort of thing. And I will be treating the test as being out of 15 instead of out of 18. Oops, there's another typo. With assignment 1, I put out the offer, and a number of students have taken me up on it, and you can still at any time take me up on it, that if you did poorly on some questions because you misunderstood what I expected there, that you can revise your answer. Go look at the answer key. It's posted, and there's with a fair bit of detail, I hope. And if you now understand what it is, then I'd ask that you go back, redo it yourself. Just don't copy my solution. Try redoing it yourself and resubmit it to me, and I'll give you 50% of the points that you lost. I'll give them back to you again. And that I know of a couple students who discovered on assignment 2 that they misunderstood what was being expected. And I've said, I'll do that on assignment 2. I'll do it on any of the assignments. So we'll make this a standing offer so there's no confusion. You don't have to get back to me immediately, sooner rather than later. And for those of you that have already sent me stuff, they know how slow I am in grading and getting back to you. So please be patient with me, but I will get it done before I submit final grades for the course. I'm not sure if redoing it will help you in future assignments because they're not quite progressive type assignments. They do build a little bit on each other, but not a large portion. And we don't have a big final exam. So if you don't master a topic, you can still progress in the course. But I would encourage you to go back and redo it because it will help you master the topics. And I think many of the topics in the course are going to be of value to you in the rest of your degree program and after you graduate. And finally, on test number 3 that's coming up this Friday, remind you, every second Friday you've got a test, and on the other Fridays you've got an assignment. So with test 3, that I'm trying to make sure that it's as predictable as I can. I don't have a huge range of things I can ask you. So it's going to look very similar to Quiz 5, Quiz 6. Most of those were relatively straightforward questions. A lot of them were, here's some data, find me the median. Here's some data, find me this, find me that. And so you're going to see a bunch like that on test number 3. There are a couple of questions on quizzes 5 and 6 that were understanding terminology and the language that we use. And there will be a couple like that on your test, though maybe different pieces of terminology than were on the quizzes. And they would be ones that were probably emphasized strongly in the 2 chapters, 5 and 6, and the 4 lectures that are associated with those 2 chapters. And so if you go back and review that and see what are things that I said over and over again, that I'm not going to pick on something that I think is relatively obscure. So the hope is that the test is very predictable and you should do well. And if you don't, then I got a real problem in making up tests. Hopefully this one is going to work. Okay. So, one other thing that I have sort of related to what I'm getting into next. We're doing value estimation right now. I posed a discussion question this morning related to value estimation because we're looking at only one particular strategy, regression analysis for value estimation. There are other approaches. It's not as diverse a mix of approaches as we'll see in classification, but there are other ways we can do it. And what I'd like you to think about is to try to broaden the way you approach problem solving, and don't think of every problem as one way you do it. There's this way. There's always multiple ways you can solve any problem. We tend in technical courses in accounting or finance or management science to say, this is the way you do it. That very often there are choices. So we're doing value estimation building a formula, and we're using a regression analysis to build that formula. Can you think of other instances where value estimation takes place, but you don't think they use a formula? And I've given the examples of, for example, a year or so ago, I had to have a property appraisal. So I had an appraiser come in and say, tell me how much my house was worth. And he inspected things, looked around, and said, okay, so how do you do this? And I'm not going to go in and tell you how he did it. I said, but I asked him, you don't have a formula? You don't say, well, if you've got a deck with this many square feet, and if your lot is this many square feet, and if your house is this age or whatever, you plug all these numbers into a formula and come up with an estimate? He said, no, never heard of that. Can you do that? And I said, oh, okay. So he had a very different approach. He didn't use a formula. Okay. That a few years back, someone rear-ended my car in a parking lot, and I had to take it in for the insurance to have it, repaired. But part of that process was getting an appraisal done for the insurance company. I didn't ask the fellow at the time, how do you do the appraisal for the insurance company and come up with an amount that they're then going to be willing to pay? How do they do it? I don't know. That they don't use a formula. They probably do some calculations, but there are other parts to it too. It's not just a simple formula. And there are lots of instances of coming up with numbers, bidding on contracts, whatever. How do they come up with the numbers? These are value estimation problems. How do you decide what your firm is worth? And there are formulas to help you do it, but is that how they make their final choice? So I'm asking you if you've got other ideas, maybe crazy ones, of how to do that. But there are other ways that may be used in different applications, and they may be better than coming up with a formula. So when we do it, and we've got a formula, that there are coefficients in our formula, there are numbers in front of the x's, that sort of thing. those are useful in causal analysis, in trying to measure what's the impact of this variable on the outcome that we want to study. And we will indirectly be looking at some aspects of causal analysis as we go through value estimation, although our main focus is on the value estimation. The input variables, we generally give them a name. We call them independent variables or explanatory variables. Statisticians like to say independent variables. Others may say explanatory. And if we can do a causal analysis and say that this explains why this happens, that makes sense. But there are many instances where the variables we can't explain what the relationship is or how A affects B. We just see that we know that it happens, but we can't explain it. The outcome variable, and we just have one outcome variable, but we have many variables we've got for input, is the statisticians will call it a dependent variable. It depends on all the other variables. Data mining people tend to call it a target variable. What's our target? What are we trying to predict? So those were key pieces of language that we had there. The method that we use in regression is generally ordinary least squares. What this means is we're trying to make the best predictions possible, but our predictions are always wrong, sometimes by a little bit, ideally by a little bit, sometimes by a lot. And we've used small errors as not being very important, but big errors as being extremely important. And so we do that by assigning a penalty to ourselves that's proportional to the square of the gap between the prediction and the actual. Whether the prediction is too high or the prediction is too low compared to actual, we look at the gap and we square that. So big gaps become really big gaps and small gaps stay small. Okay? And usually the models we build are straight line models, linear models. I don't like the word linear because lines can squiggle. When we're talking of linear relationships, we're looking at ones that are just straight lines, that they don't have exponents, we don't have squares and cubes, we don't have fractions, we don't have any of that sort of thing. It's just 5x and 3w or something or other. It's just a number times a variable. And these are nice, simple relationships, easy to explain, and they turn out to be easy to work with. Then we have the issue of quality of our model. Is it a good model or a bad model? How accurate is it? And how do we define accuracy? That we measure the accuracy in terms of standard error. That if I'm making a prediction, that standard error, I would not be surprised if my forecast was 900 and my standard error was 200. I wouldn't be surprised if my forecast was 200 units too high or 200 units too low, that the actual was as low as 700 or as high as 1100. Wouldn't surprise me at all. But it would surprise me if my forecast was off by more than 2 standard errors, by more than 400 each way. So that's a useful measure of accuracy. It makes it very concrete because it's in terms of what we're trying to predict. But probably the most popular measure of performance is this sort of global overall thing called R-square, which is defined as being that percentage of squared variation that's explained by the model. And as we indicated in Monday's class, where I had an R-square of 75%, which sounds like a really good grade, my model was giving pretty awful predictions. And I find R-square is deceiving. It always makes me think that my predictions are better than they actually are. And you've got to be cautious. I like standard error, but most people use R-square. It's up to you. Just as long as you have a sense of what those things look like. So what we're going to look at today, we're going to look at building a model. And initially, I'm going to say, let's look at the prediction errors, but I'm not. I'm going to go and do sort of what seems simple, obvious to me to do, but I'm going to go down the wrong path, and then we'll backtrack. To improve a model, figure out what you're doing wrong and fix it. So if you want to do better at something, look at your mistakes. Why did you make the mistake? What could you have done to do things better? Think about it, and then next time you're in that situation, try to make that improvement. You're always going to see that there's opportunities to make some improvement, but if we reflect on what we did wrong and we do that, we learn some lessons and we can carry those forward and do it better the next time. Same thing with model building. And our errors are those gaps between what we predicted and what actually happened. So let's not just look at standard errors and R squares or all those sorts of things. Let's just look at your predictions and see how big a gap was there between that. And looking at it through charts, there turns out there are better charts than just a simple scatter chart to understand them. We're going to be looking at residuals. That's those errors. We give them the name residuals. And we're going to look at charts of the residuals or other calculations associated with those residuals to see what we can do better. But first, we're going to do stuff stupid. So, oh, by the way, here are two residual plots, and I will point out to you, I forgot to put the discussion question in here. Here's an example of what I mean by charts maybe telling you a different story. The one on the right is our scatter chart we've used before. It's the best line is drawn through there, through the scatter, and we can see some of our predictions are, that one's pretty bad, but then these ones here look really good. You know, they're really close to the line, right along the line. These ones out here, they're pretty good too. But we've got others like there, or this one way down here, they're way above the line or way below the line. But when looking at this, we're looking vertical distance this way as we slide our head across, going from low up to high. Can't we do it in a simpler fashion? Why do I have to look as I travel up this line? And the steeper that line is, the harder it is actually to be able to interpret these things. That in part, it's because I keep measuring distance this way, perpendicular. I look at my scatter that way and not up and down. And we sort of talked about how should we be measuring these things. Visually, even though I know I should be looking up and down, I'm looking diagonally. I just can't help but look at things that way. So how about if we flip the chart? These are the errors. So here's a point that's way up high. This is above, what, 525 or so, and it's way too high. He's probably down here. It's probably this one over here, that dot there. It's the actual error that we forecasted 200 units too high. And what about this one that's way too low? Well, that's probably something, again, over about the same sort of spot. Maybe this one way down here, it's way too low. That this may be the pair that's sitting right here, that were too low. It's changing the orientation. So now I'm not looking at a line that's going up and down. I'm just looking at a horizontal line centered around zero. So on average, my errors are some above zero and some below zero, but they average out to around zero. And it makes it easier for me to look at it. And I start looking at the pattern about where my forecasts are really bad. And they seem to be really bad in the middle. They're not too bad out at this end. They're not too bad out at this end. Oh, what's this? What looks to be almost a line that's drawn here. Anyone want to try answering in chat what's happened here? Why do I have a line in my scatter? This is just supposed to be scatter, but I've got what looks to be a straight line that's sitting diagonally over on the left-hand side. Any idea what caused that? Victoria and Matt are typing. That's what my computer tells me. Some sort of base? Yeah, what sort of base? Halfway there. Victoria, have you got it? Best fit? No, that's the line of best fit, which becomes the zero line here. It's a line that goes right through the middle of everything. What's that? It's over here. Notice this. these are credit card balances. None of them are negative. We could have negative ones, that if you returned an item and you've already paid off your credit card, you'll get a credit from the bank on your credit card, but none of these ones had credits. This represented a zero balance. See, I can't go below zero. So I've got scatter above the line, but I don't have scatter below. These points here, these ones here, the scatter above, but I can't get down below because I can't get down here. So I get this odd thing. And there's a lot of them. This really emphasizes just that there seems to be a lot. It seems to have opened out this scatter here that was fairly dense. And it's a bigger scatter now this way. But the one sitting on the line, it really highlights them. When thinking about building a model here, maybe I should look at this as two groups of customers. I have customers that pay off their credit card balance and those that don't. And those that pay it off, maybe I'd like to study them separately. And then I'll study the ones that don't pay off their balance. So maybe I should be taking this whole group, or maybe the ones that carry a little tiny balance because they didn't pay all the interest or something. Maybe they're two different groups of customers and I should separate them and study them separately. Maybe I should build a model that predicts who pays theirs off and who doesn't, and of those that don't, how much do they owe? Somehow have a more complicated mix of classification and value estimation. That I don't know, but it's something to think about. It's something strange that becomes very obvious when I look at the residual plot. And we'll get back to the residual plots more today, and we're definitely going to be focusing in on them on next Monday's class. We can learn a lot through the residual plot on Monday. So the points in the line, it does make it easier to see patterns generally. And by that rotation of the axis, it really does help. And it's just the way we interpret visually things. And so again, it gets back to my old topic of communication. How do I communicate information to myself or to others in a more effective fashion? And there may be little tricks that I can do to make it easier to understand. Some things we do may obscure things, may seem like the right thing to do, but it's obscuring stuff. So let me park that for the moment and just go and take a naive approach to how to improve my model. And if I go back to the beginning, I started out and said, okay, I have a group of variables. I've got income, credit limit, credit rating, number of credit cards, age, number of years of education, a whole bunch of different variables. I looked at scatter diagrams for each of them. I looked at correlation coefficients for each of them. And from that, I decided what variables I thought were important and ones that I didn't think were important. And I thought rating, credit limit, and maybe income were going to be important. And age, number of credit cards, amount of education probably were not. Okay. So if I'm looking at improving my model, probably if I used more relevant information, I could make better decisions. So make better decisions by having more information that was applicable to my problem. And so I used rating. That was my first choice. My second two choices were credit limit and income. And credit limit was stood much higher than income. So let's suppose I focus on credit limit. Credit limit's an interesting one. It makes sense to me that those with a higher credit limit can borrow more. So they do, because you're allowed to. Those with a low credit limit can't borrow a lot because the bank won't let them. Maybe their limit is $400. So they're not going to borrow $2,000 because they're not allowed to. But the person with a credit limit of $10,000, yeah, why not? That incomes, yeah, I can understand that one too, that if I had higher income, I wouldn't be as concerned about borrowing. because I know I earn so much money, I can probably pay it off if I'm just spending everything. But credit limit is the one with the highest correlation. So let's just put it in there and then see what we get. So I'm building a linear model. So linear models have just coefficients and variables, coefficient and variable. If you did Quant 1 at St. Mary's, if you weren't from NSEC, you did that course and they did linear programming and they built linear functions, simple straight line functions, where this was the unit cost of product A and this was unit cost of product B, and this was fixed cost, and if I add it up, it's going to be my total cost. And the variables were how many I make of each of the products. Nice, simple cost formula. So what happens if I put that in there? And I'm going to do that in Excel. So we have challenges with Excel, and it's best illustrated if I go directly to Excel to show you. Oh, yes. So before class, 3 minutes before class, Top Hat wouldn't let me launch virtual classroom. And I tried restarting it and everything else. And finally, I just restarted my computer. And so, and that worked. But unfortunately, it slowed me down here. So let me take, I think this is the one we were using at one time. So let me close that out for now. I'm going to say okay, and hopefully I'm not messing myself up. Whoops. I get, okay, chapter, okay. This is a lot of junk I don't want. Let me just delete these. That was from previous class. Didn't save it, but I guess it saved it. I don't want this. And I don't want this. Okay, I think I'm back to a reasonably clean data set. Okay, so if I go in to, let me just show you quickly, and then I'm going to go back to it again, how I'm going to do things. If I go into data analysis, and I pick regression, okay, it asks for the variable I want to predict. That's my y variable. Oh, sorry, excuse me, just a second here. You get out of here, second. You get my screen set up here better. There. Makes it a little smaller, but I've still got to get back to find you, or you can find me. There, that's me. And now I need to find Excel again. There, okay. We're back together again. So I was saying I was going to go to data analysis. I picked regression, and it gave me this. So I've got the y variable. So that was balance I put in. And then it asked for my x variable. And last time I picked rating. I picked one column. If I want to pick other columns, if I want to pick income and cards or age or whatever, it only gives me one box to pick my columns. So my columns have all got to be together. And so I find it best if I'm playing and building different models, I go and just copy what I need and use it and build my model and just do each of them separately. And because we're going to be building multiple models, so I'm going to do it that way. I'm right now, I want to use, now these guys happen to be side by side. I want to use limit and rating. Okay, so I'm going to grab these, copy them, a new worksheet, and paste it in. Whoops, sorry. That's not where I want to paste it in. I want to paste it in right up here. And then I'm going to take the balance data that I'm trying to predict, and I'm going to paste it in my new sheet right up here. Okay. make this bigger so you can see. So I go up to data analysis and regression, and my y variable is in column C. So it's C1 up to C401. And my x variables, now I have two x variables. I've got limit and I've got rating. And so it starts in A1 up in that top corner, and it's going to go all the way down to B401, the bottom of the rating column. I've got labels to my columns. Generally, I do for these ones. I'm going to put all of this stuff in the same sheet. So I'm keeping all of this stuff together. Okay? And I'm going to put it all in column E1. Okay. Boom, there I go. All right. So what have I got? And make it just a tiny bit smaller so you can see everything. There you go. Now you can see everything. So I've summarized them in one of the slides, and so I'm going to jump to the slide in a minute. But first, remind you, this table in the middle, we're not using, but they would use it in a SAT scores. This portion of the table over here, we're not going to use, but they might use it in a stats course. Should also warn you, in an intro stats course, they wouldn't be doing models like this. They only look at one X variable. We're going to be looking at multiple X variables. We're doing multiple regression, we call it. And that's usually not done in a first stats course. I don't know why it's because they spend too much time on little stuff and don't get time to hit these more interesting issues. So let me go back to my slides on this, and I'll show you the output again. There it is. And I can show you other things at the same time. So this was the table that's up in the top corner of Excel output, and it was overall model performance. And then there's a table that's down here that tells me about the coefficients in the model. What's the role of rating? What's the role of limit? And so on. Our previous model was balance was minus 391 plus 2.57 times rating. That this was the coefficient for rating and this was the intercept. In the overall performance, the R square was 0.75, suggesting it explains 75% of the variation in balances. But the standard error up here in this portion of the table was 232, suggesting that don't be surprised if any predictions you make with that model for a particular customer, just one customer, those predictions are often off by $230 too high or $230 too low. Okay, that was an idea of what my precision was. So if I just look at those performance measures, look at what I've got now. R square, 0.7459. It's essentially the same value as I had previously. Adjusted R squared, which we're not using, is actually just a tiny bit lower than it was previously. My standard error is still 232. And I think it's actually a tiny bit bigger than it was previously. But the numbers are basically the same. The model is not any better at all. And if I look down at the coefficients, they've changed. So it's gone from minus 391 to minus 377. Okay, not a huge change, but still a change. This one went from 2.57 to 2.20. That's a pretty big change compared to what we had seen last class. We talked about how big a change, how far off could our estimate be. And then look at limit. It's got a very bizarre little number. But maybe that's just because credit limits are big numbers compared to ratings. Ratings only went up to 1,000, but credit limits could go up to 20,000 or 15,000 or something like that. Really big numbers. So maybe it's just a scale issue. But let's go look at this in more detail. And we're going to start out looking at the coefficients. I'm going to look at that coefficient for limit. The new value, the estimate of the roll of credit limit is 0.0245. Don't worry about it being a small number. It may be it's a small number because the limits are big numbers. So don't fuss on that aspect. Sometimes small numbers are still really good and useful to us. But the standard error is 0.06. So this means that I should not be surprised if my estimate is off by 0.06 either way. That's sort of empirical rule. But it shouldn't be off by more than twice that. But let's just look at being off by one standard error. One standard error below takes me down to 0.04, minus 0.04. So I'm saying that the correct value for limit, the correct coefficient for limit, might be as low as minus 0.04, suggesting as credit limit goes up, balance goes down. It's negative. On the other hand, it may be 0.06 higher, which translates into a coefficient as high as 0.09. So as credit limit goes up, balance goes up. You're telling me that as you increase the credit limit, maybe the balance goes down, maybe it goes up, maybe it doesn't change at all. Maybe it's just zero. It doesn't change. There's no slope. I don't know if it increases balances or decreases balances or doesn't do anything at all. There's no compelling influence that credit limit has any impact on balance. That I'd like to know, does it consistently push things down or does it push things up? But don't give me this fuzzy answer that says, don't know. Could be, maybe not. In that case, it usually means it probably doesn't tell us anything. And we'll see. That's why my model didn't improve, because it didn't tell me anything. And if we go back and look at credit limit and rating, we saw previously that they were almost perfectly correlated. That as credit limit goes up, rating goes up, or as rating goes up, credit limit goes up. I'm not saying which causes the other, but it's almost a perfect straight line. If I know one, I know the other. If you tell me your rating, I can tell you your credit limit. If you tell me your credit limit, I can tell you your rating, almost exactly. So it's knowing one tells me the other. Knowing both doesn't help. I already knew the answer. So it's telling me stuff I already knew. And so that's why it doesn't improve my model, because it's not new information. It's just the same information given to me in a different format. This seems sort of strange, that correlation, but if you think about it, how does the bank set its credit limits for customers? Because it sets them. It takes your rating, and if your rating is 500, it gives you this credit limit. If your rating is 800, it gives you this credit limit. If it's 200, it gives you that credit limit. It would appear that the bank is setting credit limits based upon the rating. That's it. So if I know one, I know the other. That we'll revisit this later and see if there was a different way we could have discovered this without having to do it this way. We still have another choice. Credit limit, that's not going to help us, but maybe income will. So what happens if we put income in our model? So to do that, I would have done this. I would have gone back to Excel, and I'm going to go back to my data, and you'll see income, and I'm going to use rating, and they're in separate columns, yeah, but I've got something in between. I just want to take income. Zoom. I go down, I grab it. I'm actually going to cheat and do this quickly. I'm going to take all three. I'm going to, put them in a new page. Where's my new page? There we go. And paste them in, and I'm going to delete the one I don't want. There we go. So these are the two variables I want to use to make my prediction. And Then I've got to get the balance data. I'm going to grab all of it. So as I said, that to do this in Excel, it's a little more work. Do it because I've got to put all of the stuff in one place together. And then I'm going to go up to data analysis, use regression. I'm going to use the same stuff I had before because it's still column C and I'm using A and B. And I'm going to click OK. I've got labels. I've got an output in that same spot. And I get a table of stuff. And there's a whole bunch there. And I'm going to jump to my slides and just show you what was there. So here's let's look at the overall first. So this was my old model, minus 391 plus 2.57 times rating, R squared 0.75, standard error 232. First, let's look at performance. R squared, it's now 0.875. Halfway between 75% and 100%. The best I can do on a test is 100%. Halfway is 87.5. So I've closed the gap, cut it in half. That's a big improvement from where I was before. I'm still not perfect, but I'm halfway there. I should be very happy. If I look at my standard error, I've gone from 232 down to 163. That's not cutting it in half. No, and it's because R squared and standard error measure things differently. It's a little tricky. It's not I've got a big improvement. There's no doubt about that. I've probably cut out almost a third of the error that I had before. I've got 2/3 left. But that's still not cutting it in half. I would have liked to have cut it in half. But I've made a lot of progress. This is quite good compared to where I was. I still would probably want to do better. And on Monday we will. We'll get further along than 162. Let's look at the coefficients in our model. So previously it was, my intercept was minus 391. Now it's minus 534. Doesn't matter. Generally, don't worry about the intercept. The intercept is just a number to make everything else work. Usually we don't focus on it when we're doing causal analysis and that type of thing. Let's look at rating. It was 2.57 before. It's now 3.95. Whoa, it's jumped quite significantly. A lot more than our estimation error was before. If you remember last class, I thought the coefficient might be off from the correct value by maybe 0.15, no more than that either way. Well, okay, this is a huge difference. It's now saying rating is so much more important than it was previously. That we have a group chat. I don't have a discussion question at the moment, if you're saying. Right now we just have chat. Hopefully everybody can see what's appearing on the chat. But look at income. With income, it's minus 7.67. It's negative. And this isn't just some fuzzy little thing. If you look at the standard error, it's sort of big. It's 0.378. But if I still went a standard error below and above, I'm still going to get minus something pretty big. I'm still going to go at least from -7 up to, or down to, for that matter, -8 or -8.5. Whichever way you look at it, it's not only is income got a big number, but it's a big negative number. Again, I said big. That's not quite right. Income is measured in thousands of dollars. Okay, so this is in part still a scale issue. Whereas limit before was measured in just dollars. So I could have a limit of 15,000 as a number in there. And so multiplying by a small number may give me something. Income here, if your income was $30,000, the number in the formula is actually 30 because my units of measurement are thousands of dollars. But anyway, it's still quite significant. It's negative. What's going on? Why is it negative? If I look at the scatter chart of income and balance that we had last class, it was a gently sloping uphill, a lot of scatter, a lot of noise, but the correlation was positive, 0.46. If I drew a line, it would be an upward sloping line. That it's a positive relationship. If the relationship between income and balance is positive, why do I have a negative coefficient now? It just doesn't make sense. Well, I have to dig a little deeper. Look at income and rating. In the table of correlations before for it, it was something like 0.76. It was a fairly big number. That the rating increases as income increases. If you have a higher income, credit rating agencies give you a better rating because you've got more money. So rating already tells me stuff about income. If you have a high rating, you probably have a high income. So I already know some things about your income. But the scatter is still pretty broad. It wasn't like rating told me exactly what you had as a credit limit. It doesn't tell me exactly what you have as income, but it gives me some idea that these two things are correlated. They're related to each other. And that is confusing us. I cannot separate out information on income from information on rating. Knowing one tells me some about the other, just like rating and limit did, but before I just threw limit out. Now I'm going to keep income in my model. I'm going to keep both variables, but they're interconnected. We call this, we have a name for it called multicollinearity. It's a very long name. But this is a very, very common problem because very frequently variables that we're looking at are interrelated. They're connected to one another. Income and age. As you get older, your income tends to increase. So I can't separate those two from each other. That there are a variety of things that are interconnected between the two. And sometimes I have variables that aren't. They're completely separate. But very frequently I've got variables that are a little bit related and some that are very, very, very related. That what happens with that is that they seem to have counterbalancing effects on each other. I can't separate the effects out. And if I'm doing causal analysis where I want to know what's the impact of income, what's the impact of rating, I can't separate them. I can't talk about one without talking about the other. And so for causal analysis, this is a real problem. For value estimation, it may not be a critical problem. I can still make really good predictions, possibly, but but I can't explain them very well. It's harder for me to explain why my prediction is what it is. I can't do the causal part of it. That's the explanation portion of it. And sometimes to convince someone to use my forecast, I need to explain it. This one, I can say that income and rating are both important factors, and when I combine the influences of both, I throw it into a formula, and here's what my prediction is. But it is problematic. That this process we've gone through, though, is very ad hoc, and we may well miss opportunities. We may miss things that we should be looking at. It doesn't give me really good direction on next steps. Like, what should I try now? What should I put in my model now? And it doesn't give me insights about a whole bunch of different things. So maybe I should go back to what I said at the beginning. If I want to improve, find out what I'm doing wrong, and then get some understanding of that, and see if you can find a way to fix that past mistake so you wouldn't make the same mistake again. And so that means let's study your mistakes. And those are my residuals. Those were my mistakes. Residuals are the errors in prediction. And could we go back and look at those and see if we could do better? So let me go backwards then. That I'm going to go and I'm going to start with the first model I had, which was this guy. Okay. And instead of doing what I did previously with this, where I just, oops, no, that wasn't limited rating. I just want the, okay, let me just do it with rating. Okay, and we'll ignore limit. Let me do analysis, and I'm going to just write on top of my old stuff. So I've got balance in column C. I'm just going to use rating, and it's in column B. And I've got labels. I'm still going to put my output in the same place. But down here, I don't know if you can see it, it says residuals, and it gives me many choices. Residuals, standardized residuals, residual plots, line fit plots. I pick residuals and residual plots. I'm going to pick those two. Okay, and click OK. It'll get mad because I'm putting stuff on top of old stuff, but I put it on top anyway. Okay, and so here was my first basic model, one I had last class. But if you look down below it, it will give me, for the first one, the prediction was $335, and it was wrong by only $2.40, 2.3997. The second one, they predicted 848, and it was off by 54. Third one, 928, it was off by minus 348. The next one was off by minus 392. These were all the errors I made. And some of them you can see are quite small, like that first one. And here's one, 480 later on. And there's some bigger ones further down as well. Somewhere, maybe it's up here somewhere. There it is. It gave me a picture of it. So I always have trouble finding where it throws pictures. So these are two useful things. We've already talked about this, but now I'd like to look specifically at this set of numbers. I want to go and explain these with the other variables I've got. Let me take these. Okay, these are my mistakes. I'm going to go and paste them into a new sheet. Okay, let me make that a little bigger so you can see it. And I'm going to go back and look at my variables and the ones I haven't used. I haven't used rating yet. The next one I was looking at using was income or limit, or cards or age or education. Let me just grab all of these. There. And where's my new sheet? It's over here. So I don't want to use rating. I've already used that one. And I don't want risk categories because those are words. So let me just delete those. So here are the variables I've got left I can play with. I can use income, I can use limit, I can use cards, age, education, and I'm going to want to predict my error. Can I guess that in this case here, I was going to be 480 too high? If I had known what their income and limit and credit cards and everything else, what are the things that give me insights in predicting? Let's go back to what we did last class. I can do scatter plots of these, which we will do next class, but I can do the quick and dirty one first, and that's all we're going to end with today is doing the quickie guy, is we're going to look at correlation. And it wants to know where's my data. It's an A1 up to F401. I've got labels. I'm going to put it in my same sheet here so I can see it. I'll put it in H1. Right up here. Boom, there's my table. Okay. And now I can look at this table and I can start looking at what, for residuals, what's correlated with residuals? Income has a negative correlation. As income goes up, my residual goes down. Now, not just down to zero, it keeps going down to negative values. Watch it, residuals go from positive to negative. But I've got a relationship between residuals, the errors, and the income. So if I knew the income, it would give me insights as to the size of the mistake. And it seems that for low income, I am overestimating. My residuals are positive. And for high incomes, my residuals are negative. So I'm underestimating, or whatever. I don't know, one way around or the other. So my estimates are too big in one case and too low in the other case, and they depend upon what the income is. So it's not saying balances are negatively related. I'm saying the prediction errors are negatively related. Look at limit. Limit, the correlation is almost zero, almost perfectly zero, meaning limit tells me nothing about the mistakes I'm making. And that's why it was of no use to put it into my model. Cards, yeah, a little bit. Age, a little bit. It's negative, probably like income is. Bet you if I put income in, then the residual left over, age, may not give me any help at all. Age and income move together. But because this is negative, that's why the coefficient in my model is going to end up being negative, because income and the residuals have a negative relationship. So this table gives me an idea of where to go next. I should be going next and putting income into my model. And from there, I'm going to get the sort of results that I just had. So as I said, its limit gives me no new information. Its correlation is next to zero. And whoops, yep, back up here. There we go. But income does look minus 0.43599 is a reasonably big number in absolute terms. So I should put income into my model. I'm going to refit it. I'm going to find the residuals. And then I'm going to go and ask, okay, does limit, cards, age, education give me any new information now? And it maybe limit does now after I adjust for income. I don't know. I'll find out when I go and do the next round. So each time I find out what my mistakes are, and I look at my mistakes, and I see, is there anything I can learn from my mistakes? And so we've learned here that that if we put income in there, we should get better predictions. So we've seen that we can improve a model by adding more variables that give us more information. Improvement depends upon whether it adds new information. It gets messy when my variables are interrelated. When I have that problem of multicollinearity, it can give me unexpected results. It can give me coefficients that go in the wrong direction, or the numbers aren't what I expected. But we're focusing on incremental improvements, and that goes by find your mistakes, try to find ways to explain or eliminate the mistakes, and then move forward and do this recursively. One time. Just keep doing that, repeating it. But there are other things we can see in those, not just correlations, but there are other things we can get by looking at the plots and looking at the residuals. We can find out whether or not we should be using a straight line or should we be using a curve. Some of that stuff we can usually pick up by looking at residuals. I can look to see if nominal variables are helpful. It's not going to be a scatter plot because I'm looking at categories, but I could use a box and whisker diagram to see if I could find a pattern in my residuals in terms of one category being different from another category. So I can, from this, sort of get some ideas on how I should be adding variables or deleting variables. I can't give you a fixed answer of what sequence you should add qualitative variables or quantitative ones, but it does become interesting in terms of how to do that. We can fit in qualitative variables. Some are very easy to do. Gender is easy, male, female, ones that are just binary. If it was ethnicity, where I've got several ethnicities, that gets a little more complicated, but I can do that too. But with all of these different sorts of things, I may be able to do it, but it can be complex. It can create new types of issues and problems. And we may not know how to fix them, but I want to make sure you're aware of those. Just sort of cautionary remarks, like we've had before, but cautionary things about reading too much into what we've got, or dealing with samples that are too small, or those sorts of things. There's some warnings I'd like to put out about regression, but it's a really good tool and it's very widely used. Far and away the most popular one for value estimation for all kinds of different types of modeling situations. Regression is the go-to. It's your standard tool in your toolbox. You're going to have a hammer and a screwdriver and a pair of pliers. In your data analysis toolbox, you're always going to have regression. It's one of those really essential tools in a toolbox. That's it for today. Hopefully the weather improves. They said by tomorrow afternoon we will see some yellow in the sky, some sunshine. So and we're supposed to have a good weekend, and then back to rain again, I think, after that. So enjoy things, and we'll be in touch again on Monday. And good luck on the test on Friday. I hope it goes better than the previous two. Take care. Bye now.